Okay, so the second part of this little sub-series, I guess you call it, is we're going to factor with multiple zeros. So we're involving factors with multiple zeros. So once you find a zero of p of x, what you can do is you can actually substitute it into the derivative to see if it is a double zero. And if it is a double zero, then you substitute it in a second derivative and it'll determine whether it's a triple zero and so on and so forth. So if p of x has 0 alpha, then check the derivative. If the derivative has 0 alpha, then x minus alpha is a double, or I should say x is a double zero, and check p double dash of x, and so on and so forth until you get nothing again. So as soon as it stops, you basically don't have a basically when this stops and you don't get a derivative value or don't get a value for your derivative that's not 0, I should add. So a value of the derivative that's not 0, then there is no more zeros, or that multiplicity stops there. And as far as you get down, so say you got to the third derivative, then that polynomial has that factor is a multiple of 3, or that 0 is a multiple of 3, or has 3 multiple, whichever way you want to think of it. So basically, this is going to be added to our tests. So factoring again. So back to our list, factoring polynomials. So you remember our list. Our list started with number 1, which was tests low positives. Okay, test low positives and whole numbers that are 0. So test your whole numbers and use that stuff. Okay, if all coefficients are integers, every integer 0 is a divisor of the constant term. So if all zeros are integers, then they are factors of the constant term. Now that's really important because it means that when you're guessing or doing your trial and error for your zeros, it means that you can only get factors of the last number. Now, test each 0 successfully. So next one is test each 0 for multiplicity using derivatives. Okay, so that will help us determine whether or not some of our derivatives, some of our zeros have more than one multiplicity. Okay, and that will knock a few out as well. Okay, then step 3 was to use the sum and product rules. And finally, if all else fails, long division. So long division is kind of like your one that you go to if you are stuck. But if the coefficients of p of x are all integers, then any integer 0 of p of x must be one of the divisors of the constant term. So if your constant term, so you've got some, p of x is equal to ax squared plus bx plus 10, then then all the zeros have to be 1 and 10, 2 and 5, or the negative, lots of them, etc., etc. So that's what that bit means. Anyway, let's have a look at an example. And the example I'm going to do is right here. We're going to factor the polynomial p of x is equal to x power 5 minus 8x power 4 plus 25x cubed minus blah, 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 blah. And we essentially want to factorize this one. So what we're going to do is we're going to go through that checklist that we had before. So the first checklist was to test some numbers. Okay, so let's just test some numbers. Let's try p of 1. Okay, so that's 1 to the power of 5 minus 8 lots of 1, 4 plus 25 to the power of 1 cubed minus 38 to the power times 1 to the power of 2 plus 28 lots of 1 minus 8. Okay, let's see if this one is a power. Okay, this one's a 0. This one gives us an answer of 0, I should say. Minus 8 lots of 1 plus 25, lots of 1 cubed. And I realize that there should be a power of 4 there. Okay, minus 38, lots of 1 squared, plus 28, lots of 1, minus 8. Okay, and that gives us 0, so therefore x is equal to 1 is a 0. Okay, let's just try another one while we're guessing some numbers. So let's try the next number, I guess, which is 2. You'll notice that both 1 and 2 are multiples of that 8 there, okay? So remembering that the multiples of, the zeros of this polynomial have to be multiples of the constant if they are all integers. Okay, so we're going to substitute this in. We get 2 to the power of 5 minus 8 lots of 2 to the power of 4 plus 25 lots of 2 cubed minus 38 lots of 2 squared plus 28 lots of 2 minus 8. Substitute that in, so thankfully I only have to replace the ones with 2, 2, 2, and 2, and that also gives a 0. So x is equal to 2 is a 0 of, and I should write of p of x to say what it's actually 0 of. Okay, so once we've done that, well, okay, let's have a look and see if these are any multiples, if 1 and 2 are multiples. Now remember, we can only have at most the number of degree, so the amount of zeros that is the degree of the polynomial. So if we have a polynomial of degree 5, then we can only have at most 5 zeros. So that's really important too, because it's sort of like an indication on when to stop. So as soon as we hit 5 zeros, we can stop. Now to test for multiples, what we're going to do is we're going to differentiate. So differentiate p of x is equal to whatever it was. So p dash of x is 5x to the power of 4 minus 8, 16 to the 4, 32x cubed plus 75x squared minus, that's 76x plus 28, okay? So what we want to do now is we want to check, well, let's start with the easy one, if that gives us a value of 0. So by substituting the zeros of the original function into the zeros of the derivative, like we said before, okay, this should give us, well, if it gives us a solution of 0, then it is considered a 0. So 1 to the power of 4, okay, minus 32, 1, oh, sorry, I didn't really explain that. So if this gives us 0, then it means that 1 has at least multiplicity 2, because it passes the original or the initial function. And so if it passes this one too, it means that it is also of multiplicity 2, because it satisfies 2 of the conditions. So the second one being it's a 0 of the derivative. In fact, it is 2, okay? So that means that x equal to 1 is part of the is a 0 of the derivative. So it means that x is equal to 1 is at least multiplicity 2. So now let's try our 2. Okay, so 2, we'll try that. I didn't want to do that. So same thing, I'm going to substitute 2 into these spots. Whoops. So 2 cubed plus 75, 2 squared minus 76, lots of 2, plus 28. Okay, and hopefully this will also give us a 0 if we substitute this in. So by replacing the 1s with 2s again. And if this gives us 0, that means that 2 is also going to be multiplicity 2. And it is, okay? So we've got 4 of the zeros so far. 2 of them are when x is equal to 1, and 2 of them are when x is equal to 2. So we only have one more 0 that we need to find, and I'm hoping that it's either going to be 1 or 2. So differentiating again. And we're going to find the second derivative. Okay, so to find a second derivative, what we do is just find the derivative of the first derivative, and that gives us the second one. So treat the derivative as the function, and then, or as the polynomial, and then find the derivative of that. So 5x to the power 4 becomes 20x cubed, minus 32x cubed becomes minus, now that's going to be 96x squared, plus 75x squared is going to become 150x, and the minus 76x is going to become minus 76, and the 28 is going to disappear because it's a constant term. Now, what we're going to do is we're going to test both of our points. So we'll start off with 1. So substituting 1 into the second derivative will determine whether or not the x is equal to 1 is a triple root or triple zero. Okay, so 20 lots of 1 to the power of 3 minus 96 lots of 1 squared plus 150 lots of 1 minus 76. And that gives us minus 2, which is not equal to 0. So therefore, x is equal to 1 has multiplicity 2 of p of x. Okay, so it means there's only two zeros. It's only a double zero. So now let's try the other one, because we're hoping that we can find that third or that fifth zero by substituting into the second derivative again. So 20 lots of 2 cubed minus 96 lots of 2 squared plus 150 lots of 2 minus 76. Okay, we're going to substitute this into our equation now, or our polynomial, or our second derivative polynomial. And we hit equals, and that one gives us 0. Okay. Now, if we were to find the third derivative and do the same thing, okay, we would know with 1 we'd always get 0 not get 0 anyway, but 2 would also not give us 0 in this case too, and you can test that if you want. But that means that x is equal to 2 has multiplicity 3 of p of x. So what this means is to factorize, okay, so factorize this, x is equal to 1 has multiplicity 2, so that means it's a double root 0, and x, excuse me, and x lots of, x is equal to 2 has multiplicity 3, so it means that at that point it's a triple 0. So, coming back up to our original equation, what we can do is we can write, so, and this is x to the power of 5 minus 8x to the power of 4 plus 25x cubed minus 38x squared plus 28 x minus 8. This is the same as writing x minus 1 squared, lots of x minus 2 cubed. And that's another way to factorize this. So by using the doubles and the triples. So if doing that derivative and finding out those doubles and triples, we can actually fully factorize something as big as a power of 5 or even a power of 8. Anything like that. Okay. Now, just to verify, I'm going to use this one. What we're going to do is we're actually going to substitute the value into this one. We're going to go this way because it's quicker for me to type in, and we're going to see if it gives us our expression in its fully factored form. So by doing this, we should get x to the power of 5 minus 8x to the power of 4 plus 25x cubed minus 38x squared plus 28x minus 8. And there it is. So that's a really, really cool way of doing that. Okay, it actually allows us to fully factorize something, and it's a very simple process by just using that derivative. Okay, so the derivative is not always used, it's not always used, I should say. like, you know, its big avenue that we've learnt about is all about changing its rates of change and stuff like that, but it also has other uses as well. And this is one of the big places where the derivative comes up, and it just really helps us factorize things like this to make life much, much easier for us. So with that being said, that's the end of this video, and we've only got one more topic left in this chapter where we will talk about something. That something is some geometry using polynomial techniques. Okay, so with that being said, I'll talk to you guys in the next one.